Welcome back to the video. So next topic is electric breakdown. So the failure or breakdown of a dielectric material is of a great concern for an engineer. So it is a failure of dielectric material under applied electrical stress. So beyond the critical value of field strength, there is an electrical breakdown due to the physical deterioration of the material. So first there is an intrinsic breakdown, and the intrinsic breakdown is due to the excitation of electrons into the conduction band across the band gap under the excessive voltage. So high accelerating force of excited electrons excite more electrons, and which in turn causes breakdown. So the impurities in dielectric will create an additional energy levels. So the increase in temperature aids to the thermal excitation state. So thermal breakdown is due to the attainment of an excessive temperature in the dielectric. So the energy loss referred to earlier has to be dissipated as heat, and if the heat dissipated is less than the heat generated, there is a progressive increase in the temperature of the dielectric, which may melt eventually. So it is said that the thermal breakdown is due to the excessive temperature in the dielectric material, and the energy loss is referred is the heat energy, and if the heat energy dissipated is less than the heat generated, there will be an increase in the temperature of the dielectric, and which in turn melts the material. So the defect breakdown is due to cracks and pores at the surface. So another breakdown is a defect breakdown, and moisture from the atmosphere can collect on the surface discontinuities and result in breakdown, and gases can collect at pores and cracks at the breakdown, and the breakdown can occur due to a gas discharge. So these are the two breakdowns, thermal breakdown and defect breakdown. And now we have ferroelectric materials. So in material known as ferroelectric materials, the dielectric constant are some 2 orders of magnitude larger than the ordinary dielectrics. So the material of a very large dielectric constants are called ferroelectrics. So the linear dielectric polarization. So when the electric field E is applied, the polarization induced P is almost proportional or linear to the applied external electric field. So here when an electric field is applied, the polarization will be proportional to the electric field, and we will get a straight line in the case of a dielectric polarization. In paraelectric materials, when this electric field is applied, the polarization will not be linear, it will be non-linear applied with respect to the applied electric external electric field E, and the polarization will be 0 when this electric field is removed. But in the case of ferroelectric material, as I said, when the electric field is applied, the polarization will be induced to the applied electric field, and the polarization will not become 0 or will not be 0 when this applied electric field is removed. So ferroelectric materials are crystalline materials that exhibit spontaneous electrical polarization, which is switchable by an external electric field. So when an electric field is applied, the material exhibits spontaneous electrical polarizations. So what is switching? So the materials can produce a spontaneous polarization by inverting the direction of applied electric field. The direction of polarization of these materials can be inverted or changed. So when the direction of application of the external electric field is reversed, the direction of polarization of the materials can also be inverted or changed. So changing the direction of polarization by altering the direction of voltage. It can also maintain the polarization even once the field is removed. Okay, so the material retains the polarization even after removing the electric field. So these materials have similarities over ferromagnetic materials, which reveal permanent magnetic moment. So these ferroelectric materials, it is similar to a ferromagnetic materials, and it will be having a permanent magnetic moment. So these materials have very large dielectric constants. So these ferroelectric materials will be having a very large or a very high dielectric constants. So Curie temperature is also known as a Curie point, which is the temperature above which a ferroelectric material loses its ferroelectricity and becomes a paraelectric material, and that is loss in spontaneous polarization. So if the ferromaterial above a particular temperature, it loses its polarization, that it becomes a paraelectric material. So some common examples for ferroelectric materials are barium titanate and lead titanate and lead zirconate titanate, triglycine sulfate and polyvinylidene fluoride, lithium tantalate. So all these are examples of ferroelectric materials, and these materials exhibit the property of ferroelectric, and the different applications for ferroelectric materials include thermistors, oscillators, non-volatile memory, filters, capacitors, light deflectors, chargers. So these are the areas where there is an where there are the applications for ferroelectric materials. And next is an assignment question. So for an assignment, you can write this question, that is, discuss the ferroelectric phenomenon with reference to the classical example of barium titanate. And you can refer the text by Callister to find write the assignment. So next is conductors and resistors. So here in this table you can see some units for resistivity, conductivity, and different units for kinetic energy, etc. So resistivity, the unit is ohm meter, and for conductivity the unit is per ohm per meter. That is the symbols are given like this. Okay. So conductors and resistors. So materials, it generally fall into three broad categories, that is conductors, semiconductors, and insulators. So conductors are metals and alloys. Gold, silver, and copper are among the best conductors of electricity. So these have very low electrical resistivities. So the electrons in the outermost orbitals, the orbitals of the atoms of a solid, determines its electrical properties. So here the electrons move freely from one atom to other. Okay, so since they carry a negative electric energy or negative electric charge, they are easily repelled by the applied negative charge and attracted by the positive charge, so the electrons will flow through them. So therefore, applying a voltage between two ends of a conductor causes an electron drift from negative to positive, and it gives rise to an electric current. And the suitable materials to act as conductors examples are the metals, some gases including neon, and some solutions of acids, alkalis, and salts in water. Okay, so resistivity, electrical resistance of a conductor of unit cross-sectional area and unit length. So a characteristic property of each material, this resistivity is useful when comparing various materials on the basis of their ability to conduct electric currents. So high resistivity of material, it will designate poor conductors, or the material will be having a very poor conductivity. So resistivity is the electrical resistance of a conductor of a unit cross-sectional area and unit length, and the unit for resistivity is ohm meters, as you can see, and the resistivity rho will be of a material is defined as the terms of magnitude of electric field across that gives us a certain current density, such as the resistivity rho is equal to magnitude of electric field to the magnitude of the current density, that is rho is equal to E by J. So where rho is the resistivity of the material in ohm meters, and E is the magnitude of the electric field in volts per meter, and J is the magnitude of the current density in amperes per square meter. Okay, so consider a material of length L and a cross-sectional area A, and R, let R be the electrical resistance. So the electrical resistivity is given, rho is given by R A by L. So here R is the electrical resistance, A is the cross-sectional area, and L is the length of the material. Okay, so when the resistivity range, about resistivity is the material property that pertains how difficult it is for electric current to flow through a material. Okay, so the insulators are materials with the high resistivity, and conductors are the materials with the very low resistivity. So generally the SI unit for resistivity is ohm meter, and some figures are seen which describes as a ohm centimeter. You can see in some textbooks it is defined as ohm centimeter. So here we can see a range of resistivity span from 10 raised to or 10 to the power minus 8 to 10 to the power 20 for the different categories of materials. So the materials for metals, semiconductors and insulators fall in this range of resistivity. And the table, you can see in this figure, the table lists the electrical resistivity at room temperature for different materials, which are important from the engineering point of view under three broad categories, that is metals from 10 to the power minus 9 to 10 to the power minus 5, and semiconductors from 10 to the minus 10 to 10 raised to minus 3 to 10 raised to 3, and insulators from 10 raised to 5 to 10 raised to 7. So the materials copper, aluminum, nickel, etc. all is fall under the category of metals, and the semiconductors like germanium, doped germanium, pure germanium, etc. fall under the category of semiconductors, and the insulators such as window glass, bakelite, PVC, silicon dioxide, etc. fall under insulators. So what distinguishes from resistance from resistivity? So resistance, it depends upon the length, the cross-sectional area, and the nature of the material, and also the physical conditions like temperature and all. So its SI unit is ohm, and while resistivity, it depends upon the nature of the material and physical conditions like temperature, and the SI unit for resistivity is ohm meter. So resistance is the value specific to the particular specimen geometry of the material, while the resistivity do not depend on geometry, and it is important to refer resistivity when comparing materials because it is an intrinsic property. Okay. So conductors, what are conductors? So the conductors are metals and alloys, and the electrical resistivity of conductor ranges from 10 raised to minus 9 to 10 raised to minus 3 ohm meter, and the electrical conductivity is the reciprocal of resistivity, and it ranges from 10 raised to 9 ohm raised to minus 1 meter raised to minus 1 to 10 raised to 3 per ohm per meter. Okay, the semiconductors, its resistivity range is 10 raised to minus 3 to 10 raised to 3 ohm meter, and they form the base for the number of solid state devices, and the resistivity is a strong function of small concentration of impurities. And doped germanium with impurity have high resistivity, or it has a resistivity of about 2 orders. So the doped germanium with impurity content for few tens per million can have a resistivity about 2 orders of magnitude lower than that of pure germanium. And insulators, it is common electrical insulating materials, for example polyethylene, bakelite, lucite, PVC, rubber, etc. And all these materials falls under insulators, and the resistivity range is from 10 raised to 4 to beyond 10 raised to 17 ohm meter. So next is the free electron theory. So in solids and conduction, in solids, the conduction properties are not a function of total number of electrons, as only the outermost electrons take part in the conduction. And in the free electron model, the outermost electrons of an atom are not bound to that of an atom, but are free to move throughout the whole solid, and these electrons have been variously called as free electron cloud and the free electron gas or the Fermi gas. So when an electric field is applied, the free electrons will get accelerated. So upon the application of an electric field, the free electrons will get accelerated, and it will be having the same potential energy everywhere in the solid, and we can assume that this constant potential to be zero. So we assume that the potential field is uniform throughout the solid. So hence we consider only the kinetic energy. So the electron theory, free electron theory, it explains the properties of materials, both metals and non-metals, like electrical, thermal, magnetic properties, etc. So the classical free electron theory in 1900, Trude and Lawrence, they proposed a theory, and according to this theory, the metals containing the free electrons, it obeys the laws of classical mechanics. And later in 1928, Sommerfeld developed a theory known as the quantum free electron theory, and according to this theory, the free electrons obeys quantum laws, and according to this theory, the free electrons are moving in a constant potential. So here are the assumptions made for a classical free electron theory. The first assumption is valence electron will be free to move anywhere in the metal, and the randomly moving electrons, it collides with the positive ions and other free electrons, and all these collisions will be elastic, that is, there will not be any energy loss, and the momentum of the free electron obeys the laws of classical kinetic theory of gases. So when an electric field is applied, the free electrons will get accelerated, and the final assumption is the mutual repulsion between the electrons will be neglected. So these are the assumptions made in the classical free electron theory. So the classical free electron theory was successful in explaining the Ohm's law about the electrical and thermal conductivities of metals and their optical properties, but it failed to explain about blackbody radiation, about the electrical conductivity of semiconductors, insulators, and the specific heat capacity of metals, and about ferromagnetism and superconducting properties. So a free electron theory, the electrons have both a particle and wave-like characteristics, and the de Broglie wavelength for an electron, lambda, is given by h by mv, where the mv is the momentum and h is the, here lambda is equal to h by mv, where the h is the Planck's constant and mv the mass of free electron, and v is the velocity of the free electron, and the wavelength is inversely related to the magnitude of the wave number vector k. This k is equal to 2 pi by lambda. So as the velocity of the electron is smaller than that of the light, we can use the classical relation for kinetic energy, that is E is equal to half mv square. So substituting these two in equation number 14.1 into equation number 14.3, we get E is equal to h square k square by 8 pi square m. So here in this figure we can see the parabolic relationship between kinetic energy E and its wave number k. So even though the variation in kinetic energy is shown to be continuous in this figure, these are in fact very closely spaced discrete energy levels. So number k will be having multiple values, that is k is equal to plus or minus n pi by l, and here n is the quantum numbers and l is the length of axis of motion. So substituting the value of k in the above equation, and its equation is equal to h square k square by 8 pi square m, we get E is equal to h square m square by 8 m l square. Okay, so in 3D solids, the free electrons can move in any direction of space. So these quantum numbers nx, ny, nz will be there for corresponding to the 3 coordinate axes. So the quantum numbers nx, ny, and nz corresponding to the 3 coordinate axes will be used, and we can replace n square as n square x plus nx square plus ny square plus nz square. So the equation becomes E is equal to h square, and in the place of n square we get nx square plus ny square plus nz square whole divided by 8ml square. So consider this problem to calculate the energy difference between the nx equal to ny is equal to nz equal to 1 level and the next higher energy level for free electrons in a solid cube of 10 millimeter into 10 millimeter into 10 millimeter. So here we have to calculate the energy difference between two levels, and here the L is given as 10 millimeter, which is equal to 10 raised to minus 2 meter, and the equation E is equal to h square n square by 8 ml square. So we substitute the values, that is h is the Planck's constant, which is equal to 6.626 into 10 raised to minus 34, and plus in the case of n, that is nx square plus ny square plus nz square, that is 1 plus 1 plus 1, and the whole divided by 8 into m, that is mass of free electron, which is equal to 9.109 into 10 raised to minus 31, and into the L square, that is 10 raised to minus 2 the whole square. So when solving, we will get the kinetic energy E is equal to 1.81 into 10 raised to minus 33 joules. So this is the energy difference between the two energy levels. So next is Fermi energy, and in this figure we can see the electron band structure found at 0 Kelvin in the case of metals, semiconductors and insulators. So the energy corresponding to the highest field state at 0 Kelvin is known as the Fermi energy, that is EF. So at temperatures above 0 Kelvin, due to thermal excitation, there is a finite probability of some of the electrons from below the Fermi level moving to levels above the EF. So if the temperatures above this 0 Kelvin, due to this thermal excitation, so some electrons will move to the levels above the Fermi level. Okay, so the probability of occupation, that is P of E of an energy level E by an electron, is given by P of E is equal to 1 by 1 plus exponential of E minus E of the whole divided by KT. So conduction by free electrons. So free electrons, it has an off state and an on state. So in the off state, when no electric field is present, so for every electron moving with a certain speed in one direction, there will be an electron moving with the same speed in the opposite direction. So this equal and opposite velocity distribution will make the solid neutral. So hence it will be on the off state, and when on the on state, and this neutral solid, neutral solid can be biased by applying external electric field to yield a net velocity in one direction. So the negatively charged electrons are accelerated towards the positive end of the field, and with this biasing, the solid conducts electricity. Okay, so the force experienced by an electron of charge E in an applied field of gradient epsilon can be equated to the force as defined as epsilon E is equal to ma. So here m is the mass of the electron and a is the acceleration caused due to the applied field. So the electrons that are accelerated towards the positive end do not increase their velocity indefinitely. They collide with the obstacles on their way, and depending upon the time interval between two successive collisions, the electrons will acquire an average velocity or average increment in velocity called drift velocity, all of which they lose during the collision. So here in this figure you can see the velocity time graph. The extra velocity acquired by an electron due to applied field is lost on collision with an impurity imperfection or phonon. So the extra velocity acquired will be lost due to these collisions. So the average collision time is tau, and Vt is the drift velocity acquired by the electrons. And the equation ma equal to epsilon E can be written as m into Vt by tau is equal to epsilon E, and Vt will be equal to epsilon E tau by m. So the flux Je due to flow of electrons is called the current density, and Je is equal to NeVt, which is equal to Ne square tau epsilon by m. So where n is the number of free electrons of charge E, and this is a form of Ohm's law. So as conductivity sigma is by definition of flux per unit potential gradient, we have sigma is equal to Ne square tau by m. So the electrical resistivity rho will be the reciprocal of conductivity. Okay, so let's see a problem. You have to calculate the conductivity of copper at 300 Kelvin, and the collision time tau for electron scattering is 2 into 10 raised to minus 14 seconds at this temperature. We are asked to calculate the conductivity of copper. So the number of, first we have to find the number of free electrons per meter cube of copper, that is the value of n. So n is equal to 6.023 into 10 raised to 23 into 8960 by 0.06354. So in solving we get 8.5 into 10 raised to 28 per meter cube. The electron charge value is 1.602 into 10 raised to minus 19 coulombs. Also the mass of electron is approximately equal to the rest mass, which is equal to 9.1 into 10 raised to minus 31 kilogram. So using the equation sigma is equal to Ne square tau by m, we get the value for n is 8.5 into 10 raised to 28 into E square, that is 1.602 into 10 raised to minus 38 into time, that is 2 into 10 raised to minus 14 divided by mass of free electron, that is 9.1 into 10 raised to minus 31. So when solving we get the value for sigma of the conductivity of copper is equal to 4.8 into 10 raised to 7 per ohm per meter. Okay, so the mean free path L of an electron is the mean distance it travels between the successive collisions. And for an ideal crystal with no impurities and imperfections, so the mean free path of the electron which it travels between two successive collisions is L. And for ideal crystals, since there are no collisions, the conductivity will be infinite, and for atoms with imperfections, dislocations, etc., their conductivity will be lower, and at temperatures above 0 Kelvin the atoms vibrate randomly about their mean position, and these vibrations can be considered as elastic waves in crystals and are called phonons. Okay, so the vibrations occurring at temperatures above 0 Kelvin are considered as elastic waves. It's called phonons. So these phonons they increase the resistivity. So in this figure, the electrical resistivity of pure copper with low density imperfections is shown. So the variation is cubic at low temperature and it changes to linear at high temperatures. So here if we nickel is introduced, the resistivity will be higher than that of pure copper. So the increase in resistivity is proportional to the amount of nickel added. Okay. So here the resistivity, temperature, coefficient of resistance, density and tensile strength of typical conductor and resistor materials are listed. So here the conductors are used in transmission lines and distribution lines, and copper and aluminum are commonly used. So, and copper is also used in electrical contacts in switches, brushes and relays, and the material possesses high electrical conductivity and high thermal conductivity, and also has a good conduction resistance and high melting point. Okay, so these are the different examples for the different properties of materials, conductors and resistors at room temperatures. So with this we come to the end of the fourth module. Thank you.